Today we are looking at section 2 in chapter 10, and we're going to talk about how to do those hypothesis tests for a population proportion. So in the last lesson, we talked about what is a hypothesis test and how to state our hypotheses and how to state our conclusion. So in this section, we're going to talk about the logic of how hypothesis testing works, and then we're going to learn how to test a hypothesis for a population proportion. So, a researcher obtains a random sample of 1,000 people and finds 534 are in favor of banning cell phone use while driving. So, in the sample, p hat, the proportion is 534 out of 1,000. Does this suggest that more than 50% of people favor the policy? Right? Well, definitely more than 50% of the sample did, 53.4%. But what about the population? Because we didn't ask everybody. So is this enough evidence to conclude that we would say the true proportion of the whole population is more or less than 50? So, what if we just happened to get a sample that had a lot of people that were in favor of it? So, in other words, would it be unusual to get a sample like this if the actual population proportion was 50% or less? So what would we need to convince us statistically with evidence that more than 50% of people are in favor of banning cell phone use while driving? That's the idea of how a hypothesis test works. So when the observed results are unlikely under the assumption that the null hypothesis is true, we say that the result is statistically significant. When the results are statistically significant, we reject our null hypothesis. So remember, in hypothesis testing, our assumption is that the null hypothesis is true. So in this case, we would be assuming that 50% are in favor of banning cell phone use while driving. Now, by getting a sample that was 53.4%, is that enough evidence to say that more than 50% are in favor? How likely is it that we could have gotten a sample that would end up at 53.4 if the actual population was only 50? So we use that idea of unlikely. And when what happened was unlikely, we say that we have found statistically significant results. So to determine if it is statistically significant, we're going to talk about probability. So our requirement that we looked at in the last chapter is that n times p times 1 minus p has to be more than 10, and that the sample size should be sufficiently smaller than the whole population, because if it's too close to the population, then we should have just sampled the whole population anyway. So in this case, 1,000 was our sample. That's definitely smaller than the population of drivers. And then when we do 1,000 times a half times 1 minus a half, we get something that is definitely bigger than 10. So that means that we can use our normal distribution model. So we can find our standard deviation, and that's given there. We've looked at that formula before in previous sections as well. And then we would want to look at our normal distribution curve and see what is the sampling distribution here and how likely is it that we would have ended up with 53.4%, I think it was. So in our classical approach, we're going to think about how many standard deviations away it is. So as we think about standard deviations, we think about our z-score. The z-score for our sample result is 2.15. So it's 2 standard deviations above the mean. So that's pretty far above. Remember that 68, 95, 99.7 rule? Well, if it's more than 2, 68, 95, it's more than 95% confident. That's kind of rare that it's going to end out in one of those tails. There's not a lot of room out there. If we got 68, 95, there's only 5% combined in those two tails. That's not a great chance that we would have ended up in one of those tails on accident. So according to that, we would say, yes, we have enough evidence to believe that the proportion of people who would like cell phone use banned while driving is more than 50. So this is the picture of what that looks like. The area under that curve at above the 2 standard deviations is only 0.0228. That's so tiny. So there's only a 2% chance that this sample happened on accident. So we'd have to believe that the proportion is actually higher than 50%. So we're going to go through the classical approach as well. So if the sample proportion is too many standard deviations, we reject that null. And how many is too many? Well, that depends on how confident we want to be, right? So we've got that 95 is a pretty good measurement, and that's right at the 2 standard deviation line. So that can be a good measurement for us. Another way to determine whether or not we should reject the null hypothesis is with what we call a p-value. That p stands for probability. So the p-value is the probability of observing a sample statistic as extreme or more extreme than the one that we got, assuming the null hypothesis is true. So what is the probability that this happened if the null hypothesis were true? And this is the approach that we're going to be taking for the most part, is this p-value approach. So if the probability of getting a sample statistic as extreme or more extreme than the one obtained in our sample is small, then we're going to reject the null hypothesis. If we find out there's only like a 1% chance that this sample happened, we're going to say, that's pretty unusual. It's pretty rare, so I think that might be enough evidence for me to change my mind. If we find the probability of getting a sample like this is 32%, well, that's not very rare, so I don't think you've convinced me to change my mind yet. A second criterion we could use is how likely it is to determine that sample. And so that is the idea of the p-value. So this just kind of reiterates what I had just said. Okay, so in this p-value, we're looking at the area underneath the curve there. So assuming that the population was at 50%, we've got that 50 right in the middle. The 0.534 is where our sample came in, and what we want to look at is what is the probability that we end up in that tail more than the 53.4%. So we want to say, what is the probability out in that tail? And the probability out in that tail, according to this computation, with our z-score is 0.0158. That's like a 1.5% chance that this sample happened on accident. I don't think this sample was an accident then. So we would reject our null hypothesis in favor of the alternative. And we'll look at how to find these values on StatCrunch. So just some things to remember. Our point estimate of our population is given by the sample proportion, which is X, the number of observations that have the characteristic, divided by N, the number in our sample size. That's our point estimate of our population. And remember, we have our standard deviation formula there. And then remember that we should have a simple random sample, always the best policy. Have a simple random sample. We need to have that NP1 minus P be more than 10. And if it's not, the easiest way to fix that problem is to just sample more people, because then N is bigger, so then you're multiplying by a bigger number. And so that's the best way to fix that problem. If your NP1 minus P is too small, just take a bigger sample. And then the last one is that the sampled values need to be independent of each other, which is on the flip side, don't take too big of a sample, because if you're going to get too close to what the population actually is, then you should have just done the whole population. Otherwise, they start to depend on each other. So this gives us those literally same 3 characteristics that we just looked at again. So a little bit repetitive in our slides here. So these are our null and alternative hypotheses, again, that we talked about in the last section. So we have our two-tailed. The difference here compared to the last section is that in this section we are specifically talking about population proportions. So our variable is P, okay, for that population proportion. And so our null hypothesis is that the population proportion is whatever we have historical evidence to show that it is. And then our alternative is either that it is not that it is less than that, or that it is more than that. We're going to select our level of significance. Oh, and going back to this, these are the order of the steps that you have to do hypothesis testing. The first thing you have to do is make your hypotheses. You have to decide what your alternative hypothesis is going to be before you begin collecting data. So, make your hypotheses. Then decide how much evidence is it going to take to get me to change my mind? And that's our level of significance, or alpha, which is our probability of making a type 1 error. Remember, the type 1 error is kind of like sending an innocent person to jail. So it's a pretty big deal. So what are we comfortable with for a probability of that happening? Are we comfortable with a 10% chance that an innocent person goes to jail? A 5% chance? A 1% chance? How strict do we want to make our test? Courts, not for like deciding innocent or guilty necessarily, but when significance tests are used in court, the standard is a 95% significance to determine if something has been proven. Then we would compute our test statistic, which is a z-score. So remember, z-scores, we're looking at the difference between our assumption in our sample, and then we're dividing by the standard deviation, that big ugly square root thing. That's our standard deviation there. Dividing by the standard deviation. That tells us how many standard deviations we are away from our mean. Are we 1 standard deviation? That's 68%. That's not tons. Are we 2? Now that's getting up to 95, and now we're starting to get into the realm of rare if we are more than 2 standard deviations away. So then we would decide what is that critical region. For a two-tailed, since we said it's just different, I don't know if it's more or if it's less, we're looking at both tails in that graph then. Left tail, we're only looking at the lower side, and right tail, we're only looking at the upper side. And then we would compare our values. Now this says by hand, step 3. We're not going to do it by hand, but that is what we would do. And we're going to use the p-value approach. So then what we would want to find is what is the probability out in either both tails if we're doing a two-sided, one tail, or the other if we're doing a one-sided. And StatCrunch will give us that probability. So technology, step 3, we're going to use a statistical spreadsheet or StatCrunch to give us this information, but you can also do this on just a regular graphing calculator. You could Google how to do it in a graphing calculator, or really any of the other Minitab Excel, and doesn't list Google Sheets, but I'm sure you can. I don't know how, you'd have to Google it, but I'm just going to use StatCrunch because that's connected to our textbook, so that's the easiest way for us. If our p-value is smaller than our alpha value, we're going to reject our null hypothesis. So if we decided 5% is my comfort level, so if we decided we're going to go at an alpha 5 level, that's a 95% confident that we're making the right choice here. If we get a p-value that's smaller than that, like 3, we say, I was okay with 5%, but 3%, that's too rare. I got to reject the null. So if our p-value is smaller than our alpha level, we reject the null hypothesis. If the p-value is bigger than the alpha, we do not reject the null. Remember, we don't accept it. We don't say innocent. We say not guilty. And so then we would state our conclusion. Okay, so I'm going to bring up StatCrunch so that we can see how to put this in there. So in 1997, 46% of Americans said that they did not trust the media when it comes to the news fully, accurately, and fairly. Okay, so in 2007 now, so 10 years later, a poll of 1,010 adults nationwide, 525 said that they do not trust the media. So at an alpha 5 level, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. Okay, so first thing we would want to consider here is what are the hypotheses. So the null hypothesis would be that the proportion is 46%, because that's what it was the last time that this was tested back in 1997, and our null hypothesis is always the status quo. Nothing has changed. So our null hypothesis would be that P is equal to 0.46. The alternative hypothesis is given by this last statement here. Is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased? That's the key word, increased. So our alternative hypothesis then is that P is going to be greater than the 0.46. And they gathered some data, and so now we're going to go into StatCrunch, and I'm going to go into Stat. We're doing proportions. We have one sample, and what we have is a summary. Okay, data would be person 1, yes, person 2, yes, person 3, no. We don't have that. You're probably never going to have that. Maybe, rarely, they would give you that. In general, we're going to be going with summary. So I'm going to come with summary. Pull that up higher so we can see it. Number of successes, that's how many people have the criteria that we're testing here, which is not trusting the media. So it says 525. And then next is the number of observations. That's how many people in our sample. That's 1010. And now technically before we do this, we should test that NP times 1 minus P. So if I just grab a calculator and do N times P, which is 0.46, times 1 minus P, I get 251. So definitely bigger than 10. So we're good to go with this process. Now, in the last chapter, we went down here and did a confidence interval. In this chapter, we're going to leave it at our hypothesis test. And our null hypothesis is that the proportion is 0.46, and it forces those to be the same. So remember in the last section, I emphasized that those have to be the same value. StatCrunch won't even let you try to make them different values. But we do still need to choose what kind of alternative hypothesis we have. And in this case, we are testing the claim that it has increased. So we're going to use a greater than. Once we have that set, we're going to go ahead and click compute. It gives us our count and our total, our sample proportion. So in this sample, it was 52% that said that they don't trust the media. That definitely seems like more than 46, right? So then we come over here, we look at our Z-stat. Z-stats, again, tell us how many standard deviations out. So we're over 3 standard deviations, almost out to 4. So remember, 68, 95, 99.7 is 3, and this is almost out to 4. We are way out in that tail. So this is really rare. How rare is it? Our p-value is smaller than 0.0001. Our p-value is pretty much 0. The p-value is like the probability that this sample could happen if the null hypothesis were true. This says it is pretty much impossible for this sample to happen if only 46% of Americans distrust the media. That's pretty strong evidence. So we are going to then state our conclusion by saying that we are going, let's see, I'll slide through here. So this is where we tested that NP1 minus P thing. So that's good. And then they did those calculations by hand to find P hat, 52, it's right there. The test statistic Z is right here. It's slightly off to that second decimal, but that's because of rounding stuff. And then they use the Z. We'll come over to the p-value approach. The p-value, it says, is approximately 0. It's less than 0.0001. So since the p-value is less than our level of significance, which was 5%, it's less than 5% that this could happen, we reject the null hypothesis. So in conclusion, we say there is sufficient evidence at the alpha O5 level to conclude that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. we can't really, using this, make a claim as to what percentage of Americans distrust the media. For that, we would want to think back to the last section. And in the last section, I'm going to go and edit this. In the last section, we talked about those confidence intervals. So if we're using an alpha O5 level, that's like a 95% confidence level. If I do a confidence interval, then I'm 95% confident that the proportion of Americans that do not trust the media to report fully and accurately is between 49 and 55. So if it's between 49 and 55, well, the original claim was that it was, like 46? That's not in that window. So this would be another way to think about a hypothesis test. If 46 was in the window, then we'd say, yeah, it's likely it could happen. It could still be 46. But 46 is not in this window of 49 to 55. We are 95% confident from this information that the proportion of Americans that distrust the media is between 49 and 55%. Okay? So confidence intervals can tell us an estimate of what the parameter is. Hypothesis tests can tell us, have things changed? Okay? So that's how those two kind of play together there. And then the levels are complements of each other. So if we're testing at an alpha O5 level for a hypothesis test, that's a 95% confidence interval. Okay. All right, so see if we had another example to look at in here. Okay. Oh, small sample size. We're not going to do those. We are only going to look at problems that have a large enough sample size. So in this case, the idea of what is large enough, well, the idea of large enough comes in when we do that NP 1 minus P. If that's smaller than 10, then we can't really use a normal distribution. So then we would have to use something else called a binomial distribution. And we talked about binomial probabilities before, but we are not going to address that in this section today. So given that, your NP times 1 minus P should always be bigger than 10. In the problems that you're assigned, you're always going to have large enough samples. Okay, so let me know what questions you have about confidence intervals and hypothesis tests, and I am happy to answer those for you. Talk to you again soon.